I'm Robert Kirshner, and I have a lot of titles, actually. I don't know which one you want. I am Clowes Professor of Science. How about that? Science. Here at Harvard University. I'm really an astronomy professor. Or if you look out at the nighttime sky, what you see right away are a few bright things that are planets in our own solar system, but or possibly the moon, which is a terrible thing. We hate to have the moon because all that reflected light makes the sky bright, makes it hard to do astronomy for distant objects. So the real black belt astronomers don't like the moon, don't like the planets very much. But if you go out at night, you'll see stars, and the stars that you see emitted their light tens or even hundreds or thousands of years ago. The speed of light, which everybody thinks is so fast, is really extremely slow, and it's what lets astronomers see back into the past. So, for example, the speed of light is a foot. That's a unit of distance used here in the United States, and I believe also in Myanmar. It's a foot in a nanosecond, a billionth of a second. So you never see things the way they are. You always see the past. You always see light that bounced off somebody 10 nanoseconds ago, or in the back of a big room 100 nanoseconds ago. When you go outside, you're seeing light that was emitted, the sunlight was emitted 8 minutes ago, light in the solar system maybe up to an hour ago. And when you look at the stars, even the nearby stars, even the bright stars, the light has been traveling to you for tens of years or hundreds of years or even thousands of years. So without a telescope, you can see into the past a few thousand years. And what happened in the 1920s was that people began to realize that the system of stars that we're in, which is the Milky Way galaxy, we'd call it today, which we see as a band of light in the summer sky because we're looking at this system, which is a big flattened system, kind of like a pizza seen edge on, except we're a pepperoni, you know, we're on the pizza. And so our view of it is really quite awkward. We don't have a good perspective of our own Milky Way galaxy. But we know now that it's, roughly speaking, 100,000 light years in dimension across our Milky Way. So that means it takes light 100,000 years to travel across that span of distance. And that's really just the beginning. What people discovered in the 1920s was that our galaxy is just one of billions of galaxies out there. The distances between the galaxies are a few times their own diameter. So if the galaxy is, you know, this big, then the distance to the next galaxy is kind of 10 times the size of a galaxy. So if this is 100,000 light years, the distance to the next galaxy is a few million light years. And that's fairly accurate. The galaxy that you can see, there's one galaxy that you can see without a telescope, if you know where to look, with binoculars, easy object in a small telescope, and that's the Andromeda galaxy, M31. And in the autumn sky, you can pick it out. It's a kind of fuzzy patch. And what we know is that that is as big a system as the one that we live in. It's as big as the Milky Way. It just looks like a little tiny fuzzy patch because it's so far away. And that's really just the beginning. That's our local neighborhood, a few million light years away. Turns out that with modern telescopes and the best instruments and the better detectors we have today, it's not that hard to see things that are a few billion light years away, or to measure the light from them anyway. So that's 1,000 times farther away. It means the objects appear 1,000,000 times dimmer. But what has changed over time is that we have big telescopes that collect a lot of light, and we have detectors that are nearly perfect at measuring the light and turning it into an electronic signal. So very similar to the detectors that are in digital cameras and so on. They're made of silicon. They work pretty much the same way. But we take long time exposures and we add up the data very carefully. Anyway, we're able to make this, the technology has enabled us to make this leap so that we can study the distant objects. And the reason why we want to do that is that the telescope is really a kind of no-nonsense time machine. It lets you see the way things were in the past. Of course, it doesn't let you see into the future. It only lets you see the past. But we can do that to distances of 1 billion light years, and even with some effort, to many billions of light years. And that's important because the time since the beginning of cosmic expansion, since the beginning of the universe as we know it, the time of the Big Bang, we think is about 14 billion years ago. So the biggest distance that light could travel in that time is about 14 billion light years. And we can see things most of the way back. That means we're not just guessing that the universe has changed over time, the universe has expanded over time, has it gotten elaborated over time due to the action of gravity pulling stuff together and stars making more complicated elements, and all that stuff that's happened over the past 14 billion years is not just a story, it's a real history that we can observe. So stars have a lifetime, it's very long compared to ours. So, stars seem permanent. For poets, stars are kind of symbols of permanence. The speed of light is a symbol of something going fast. But for astronomers, the speed of light is slow. That's what lets us see the past. And the stars are not permanent. They're changing over time. It's just the time scale is much longer than human lifetime. So a star like the sun gets its energy from nuclear fusion. Down in the center of the sun, hydrogen, which is what the sun's made out of, is being converted into helium, the next element up. And when you do that, when the sun does that, it generates energy. Energy is released because the helium nucleus has a little less mass in it than the ingredients, the hydrogen nuclei that went into it. So hydrogen goes in and helium comes out, and the difference shows up as energy. You know that equation that Einstein has, E equals mc squared? That's not just a symbol of scientific inscrutability. That is actually an equation where the thing on the left is equal to the thing on the right. The amount of energy that you get out is equal to the change in mass times the speed of light squared. Well, the speed of light's a pretty big number, and when you square it, it's big. And that means you get a lot of energy out from a small change in the mass. This is really important. So this is nuclear fusion. This is how the sun works. And since the sun is made of that fuel, it can last for a very long time. We think the lifetime for a star like the sun is about 10 billion years. So the sun formed about 5 billion years ago, and along with the planets, like the one we're on. And it has about 5 billion years to go. So, check your homeowner's policy, but I think we're going to be okay for a while. The interesting thing is that the more massive stars have shorter lifetimes. So a star that has 10 times the mass of the sun has a lifetime that is not measured in billions of years, but only millions of years. And the very massive stars have very short lifetimes compared to the age of the Earth or compared to the age of the sun. So that means that there's a kind of a complicated story. When stars form, the massive stars live fast, die young, blow up, it turns out, at the end. They explode as supernova explosions. There's another path that also leads to explosion, where a star uses its fuel and crunches down in the center to become a white dwarf, which is a very dense kind of star that is left over after an ordinary star has used its nuclear fuel. The sun will probably be a white dwarf 5 billion years from now. In between, it will have become a red giant. It will swell up and it will vaporize all the planets. So, if you're worried about this sort of thing, you should worry. It'll heat up the Earth, boil off the oceans, melt the mountains, all that apocalyptic stuff will happen. But anyway, the lifetimes of stars are finite. The massive stars live short times. And the thing that's left over from a star like the sun is this white dwarf, which it turns out is actually a thing that is held up by quantum mechanical forces. It's stable if it's left to its own devices. And the white dwarf that is left after the sun has burned out, this kind of ash, this clinker that's left over, will last indefinitely into the future. Except some of these white dwarfs, a lot of stars are in binaries. So the sun is a single star, it's all by itself and has a few planets around it. But there are other stars that when they're born, are born in multiple systems, in a litter, of other stars. And it's interesting because the other star can affect what happens. For example, if there's a white dwarf in a binary system with another star, some mass from that other star, when it swells up to become a red giant, can fall onto the white dwarf, and it turns out that can make it explode as a thermonuclear bomb. So there are stars which, left to their own devices, will be fine, but in these binary systems, they will explode. And so there's a particular kind of explosion, these thermonuclear supernovae, these exploding white dwarfs, which have turned out to be incredibly important for measuring the size of the universe and for learning what the history of cosmic expansion has been. So it goes something like this, that we judge the distances to objects from their brightness. You can go outside at the seashore and you look out, and you see that there are ships out there, and you can't really see much detail at night, but you can judge which are near and which are far from the apparent brightness of their lights. And in something like that, you can use the brightness of objects to judge their distance. The trouble with that is it only works well if the objects really are the same brightness. Otherwise, if you have something that's intrinsically very bright, you'll think, oh, it must be nearby. And if something is intrinsically faint, you'll say, oh, that must be very far away. So if you have objects of different brightness, it's much, much harder to sort them out. And it turns out that these exploding stars, these thermonuclear supernovae, the ones where a white dwarf blows up suddenly, and for a little while shines as brightly as about 4 billion stars like the sun, these things turn out to have a fairly narrow range in brightness. They're not all exactly the same, but it turns out it's even better than that. By studying them, we can tell which ones are the 100-watt bulbs and which are the 50 watts and which are the 25-watt bulbs. We can actually measure other properties of the explosion. And that is extremely valuable. So they're very bright. They have a narrow range of brightness. And when we see a supernova like that, we can measure how bright it appears and figure out how far away it is. This is very good because we want to figure out what the universe has been doing over time. What we know is that the universe is expanding. People have measured that nearby galaxies are moving away from us. More distant galaxies are moving away from us more rapidly, as if the whole universe is expanding in all directions. And we think that this is the result of, or anyway, the aftermath of the Big Bang, this sort of beginning of cosmic expansion about 14 billion years ago. And what we're trying to do is to figure out how it's changed over time. Has the universe expanded at a constant rate? Has it been slowing down due to gravity, as everyone expected it to? Or, as was, I don't want to spoil the suspense, but what we found is that the universe is actually speeding up, which is very mysterious. So, the supernovae are really important because we use them to measure distances. If you can figure out the relation between velocity and distance, that is, the expansion and time, you can actually trace the history of cosmic expansion. So in the 1990s, everybody thought that we would be able to use the supernovae to measure the slowing down of the universe, because there had to be enough matter in there for the universe to be just bound and slowing down. Everybody kept telling us that's what we would find. So we started to make the measurements, and it was kind of interesting because the other group, the LBL group, published a result, and they said, the universe is slowing down. We've measured it with the supernovae, and it seems to be slowing down. So that seemed good, except when we did our analysis of our data, we found that it didn't seem to be slowing down. So this was very awkward. We didn't know what to do. We thought, well, maybe we've made a mistake or something. I don't know. But as time went on, going from 1997 into 1998, both teams started to talk about their results. And both of us saw that in our data, things were not slowing down. It's as if the universe had been speeding up over time. So it was slowing down at the beginning, I suppose. But then there's been a switch from slowing down to speeding up, a kind of acceleration in the expansion of the universe. Well, this was a big surprise to us, but it's something that people had been talking about and had been thinking about actually for quite a long time. Turns out Einstein, when he first applied general relativity to the universe, thought that the universe was equal to our Milky Way galaxy, because people didn't know that these other galaxies were out there. So when it came time to construct a model, a theory for how the universe would expand over time, he thought static would be a good kind of expansion, no expansion, that would be good. And he knew that if he had gravity, that things would clump up, so he put into his equations another term to make things kind of a static universe that was this so-called cosmological term, or cosmological constant. And there was no real reason he did it, except it made it kind of easy to think about the universe as having a kind of finite volume, and it avoided some technical problems, and it made a static universe. But what astronomers found in the next decade was this business of the galaxies rushing away from us, the expansion of the universe. So at that point, say in the 1930s, Einstein said, well, forget the cosmological constant, if it doesn't serve its purpose, then let's not talk about it. But it does have this quality of making things speed up. If there's the modern way to talk about it is as if it's an energy associated with empty space. So, in quantum mechanics, there are a lot of weird things, and one of the weird things is that if you look on smaller and smaller and smaller scales, the uncertainty in the energy gets bigger and bigger. And that means you don't know when you're looking at a little tiny piece of space whether it might have in it a particle and its antiparticle that kind of get created out of nothing and then annihilate. On average, the value is zero, but the fluctuations are big. That's what the quantum mechanics tells you. And the idea is that there could be, the vacuum is not just emptiness with no properties, but it could have these sort of interesting properties. And that's the modern theory of electromagnetism, is like that, with particles and their antiparticles being created and destroyed all the time. And that picture fits the data, which have been exquisitely measured in laboratories on the Earth, much better than a picture where the vacuum has no properties. So this would be something similar for gravity. Now, nobody knows how to do this. Nobody knows how to make a proper quantum theory for gravity. So making the right prediction about what the properties of empty space ought to be is a little tricky. If you do it more or less the way people have for other forces in nature, it turns out you get a really bad answer, because the energy associated with the vacuum gets big as the length that you're looking at gets small. And it turns out that for gravity, the appropriate length is so small, and the energy that is associated with that is so big that people have known since the first time they wrote this down, that the universe isn't like that. So what this says is the cosmological constant is very embarrassing to theoretical physicists. The number they got was, first of all, Einstein had said it was a bad thing. Then when you did this calculation, the number they got was way too big, like 10 to the 60th instead of 0.7, which is really bad. So for a while, people just didn't want to talk about it, and they didn't want to think about it. And they thought, well, if it's not infinite, and it must be zero. So that was one way to deal with it. And for an observational astronomer like me, the idea was not to worry about cosmological constant, because we thought we were going to measure slowing down. Anyway, we measured cosmic speeding up. The natural way to get that is to have an energy associated with the vacuum that's like the cosmological constant, that can make the universe speed up over time And that's the idea that people have used as kind of a beginning to think about how to understand these observations, that we really see a universe that's expanding faster now than in the past. So the idea is there's something, we can call it the dark energy, that resembles Einstein's cosmological constant, more or less, that is really propelling the universe, that's making it expand. The trouble is, we talk about it, but we don't really understand it very well. We don't know. So if you do a calculation of what is the value of that number, you get a very wrong answer. So that's telling you something's not right. And there are plenty of other possibilities. It doesn't have to be constant. There could be something that changes with time, and it could be the dark energy could be any of a very large number of things that people have thought of. So there's this kind of vast, weedy garden of ideas that people have thought of. Well, what about this? What about that? What about the other thing? And as an observer, what you want to do is do the best you can to put constraints on this and kind of weed out the garden, show that some of these ideas are wrong, and people shouldn't waste their time pursuing them. The idea is with the observation, from the observational side, is to kind of weed out this garden and find out which ideas are right, or anyway could be right, and show which ones are wrong so that people don't waste their time working on those. So that's where we're getting with this. We've seen the effect. The universe has been speeding up in the last 5 billion years or so. We've also looked far enough back into the past to see that the universe was slowing down before that, so that's good. That's a prediction of this kind of gravity and dark energy picture, is that if you look far enough in the past, gravity should have been winning, that density should have been higher. So, things sort of fit together, but there's this very bad feeling that everybody has that we don't understand in any basic way what this dark energy is. What's more, there's no physics experiments that you can do. There's no laboratory experiment that you can do, or that people have thought of yet anyway, that really tells you whether this idea is right, what the properties of the dark energy really are. So it's a very interesting thing where in astronomy, we see the effects, we talk about it as if it's real, and we can try to pin down what the properties of the dark energy are. Is it like the cosmological constant? Does it change with time? That's a good question. We can try to work on that, and we are working on that. But there's no laboratory experiment. It's kind of a funny sort of thing where only the astronomy is telling us about this very big phenomenon that turns out to be very important. It's 2/3 or maybe 3/4 of the universe is in this form of the dark energy. So that's really weird. And we've discovered, 3/4 of the universe in the last 10 years. We don't know what it is, and there's no laboratory experiment that helps us kind of sort this out. Right. Well, we're very good at observing the past, and telescopes really let you see light that was emitted 10 billion years ago. We do not see so clearly into the future. So, if you make a prediction about what the universe is going to be like 1 billion years from now, it's a little harder to test it. Nevertheless, if the dark energy is really just the cosmological constant, and there are no surprises, or another way to say it is, if the latest picture that we have in the last 10 years is absolutely perfect, which, a certain kind of modesty is probably a better policy, but never mind that. If we've got the whole story and we know exactly what the dark energy is, then you can predict what the expansion of the universe will be in the future. And it will be literally exponential expansion. That means the rate of expansion will depend on how big it is. It'll go faster and faster and faster. It's like compound interest or any of those things that kind of get out of hand. The expansion of the universe will get out of hand. And what that means for astronomy is that distant galaxies, which are moving away from us at a fairly large fraction of the speed of light, will be moving away faster and faster. Their light will get redshifted. That means that the light gets stretched out to longer wavelengths and they get dimmer, and eventually we just won't be able to see them. So what will happen is, as time goes by, the distant galaxies will kind of go beyond the horizon for us. We won't be able to see them. Another way to say it is that the piece of the universe that we can see will kind of shrink in, and we'll have fewer and fewer things in it until finally, until, if you follow this idea far enough, it would just be us and the Andromeda Galaxy, and we'd be whirling around, and eventually we'd collide with one another, and there'd just be one galaxy, and that would be the whole universe. And what's so funny about it is that is the picture that Einstein started with, that the Milky Way galaxy was the whole universe. We'll have come full circle. Also, it will be impossible at that date in the long distant future, 50 or 100 billion years in the future, it will be impossible for astronomers to sort this out because there won't be any galaxies for them to observe. So that's why we have to do this now. That's why increasing astronomy budgets in the coming decade is really an important thing, because in 100 billion years, it will be impossible in principle to make these measurements. So the timescale, the age of the universe now, we think is about 14 billion years. So the universe has been expanding from this hot, dense state in all directions, the Big Bang. And it's been elaborated over time. Gravity has made things clump together, so galaxies have formed, stars have formed, stars go through their life cycle and they emit, as they blow up as supernovae and put out heavy elements that are used by the next generation of stars, and they make the planets. You have in your bones calcium atoms that were manufactured in supernovae. You have iron that's in your blood, the air that you're breathing. Those nuclei, those actual atoms, came from stars that blew up before the sun formed. So you're really part of this whole story, part of the universe. So that's the story that we know has been going on in the past. The piece in the future is much, much harder for us to say with confidence, because after all, there's always that big voice that, astronomers know the universe began in a powerful explosion 14 billion years ago. And that's the voice in the planetarium. And it's the voice of authority. And it's the voice of conventional wisdom. And we always talk like that. The trouble is, what changes is the thing we say, So now we say, and the universe is expanding faster and faster. Well, okay, that is our current picture. That is what we know. And, we're trying to tell you the right story. But it would only take some very teeny deviation from the cosmological constant as the dark energy to produce a completely different effect. So if there's some slight, teeny little difference which we haven't been able to measure, it could mean that the universe will expand for a while and then collapse in the future, or expand faster than exponential, in which case things will completely get ripped apart. All of these weird things are possible, but our ability to measure them is really quite limited. So, probably it's better for us to be a little bit more modest about what we do know and what we can predict and what we can be sure is really going to happen. But I think we're in a very interesting state where the evidence has gotten better over time that we really live in a universe that's really accelerating. The implication is that there's this stuff, this dark energy, really a negative pressure or something or other in the universe, but something that is related to the nature of gravity that we really don't understand. There's a big piece of fundamental physics that's missing. And this, in a way, is great because, it's when you know everything and when everything's understood and it all fits together, that's sort of the sign of something that's done. And you move on, do something else. When things don't fit together and don't quite make sense and there's a problem here, that's great because, of course, it means there's going to be progress on this subject. The trouble is, we don't know when. We don't know, and we don't know which idea at the moment. We don't know which of the many ideas is really going to be the one that helps us solve this problem. It probably will seem like a nutty idea when it's new, when we first hear about it. But that doesn't mean that all nutty ideas are right. It just means that we have to figure out which of these things is really right. And to do that, we want to do big surveys to measure more precisely how the universe has been expanding. We want to measure more precisely how matter has clumped together under the force of gravity. We want to study this history that's available to us using telescopes to really see what the constraints are on this weird thing, this dark energy that seems so important, but that we really have very little grip on. We have very little grip to tell which ideas are right and which ideas are wrong. And really that's what science is all about, is to pick out from the speculation and the kind of imagination which things agree with nature. And so far, the measurements that we've made are kind of crude, and we've got to do better. Yeah, people often ask that. I give a lot of public talks, and there's always somebody who stands up at the beginning and says, okay, they say, well, I've got you now. What happened before the Big Bang? And of course, the answer is, it's not like we have some complete special knowledge and that we're forcing you to believe it. We're trying to puzzle this out. There is a time over which we really do understand the physics pretty well. And it goes surprisingly far back. That is, if you take a particle accelerator on the surface of the Earth and you smash together protons and antiprotons, under the border of Switzerland and France, and you are creating conditions which are like the ones that existed in the universe very, very early, in a very small fraction of a second after the Big Bang. So I'm not saying we know our way all the way back to the beginning, and there are some mysteries there about exactly what happens when the density gets very, very high, and what happens when the distances are so small that we really can't predict what is going to happen. So there are limits to our current understanding of physics, but they are way back toward the beginning, and there's nothing that says that we won't eventually understand more and more of it. So that's kind of an evasive answer, I know that, but the fact is this idea that the universe was very dense, very hot at this early time is something for which the evidence is very strong. And by pushing our current understanding of physics farther and farther back, we're going to understand more and more of it. So it's a real adventure. And that piece of it, we really do have a program to study. The smashing together of particles in laboratory experiments really is creating conditions that were something like what was present back then at the time of the Big Bang, and will help us understand the universe on the big scale. So there's this very interesting idea that by looking on the very smallest scale, the smallest, tiniest fraction of a millimeter that we can do, we learn about the universe on the very biggest scale, the scale of the galaxies and the hundreds of millions, even billions of light years. So the interesting thing, or one interesting thing, is that our understanding of the physical world is all of a piece. The understanding the things on the smallest scale is really how we try to explain what's going on the biggest scale. Well, I can tell you something about the discovery of the cosmic acceleration, which was that Adam Rees, who was a postdoc who had been my student, he was out of Berkeley, and he was doing the data analysis, and he'd call me up on the phone, he'd say, this is kind of funny because I'm getting negative mass, as if the universe is not slowing down but speeding up. And I said, well, Adam, there are lots of ways to go wrong, and you in your heart, I said, it's wrong. So, my approach to it was prejudice, unwillingness to pay attention. I just assumed he'd forgotten to divide by the square root of pi or, something, and that we would find this mistake and this thing would go away. And when it didn't go away, It meant that we were, first of all, we read the paper from the other team. They said the universe is slowing down because of the measured by the supernovae. So we had to go against that. We also had to go against the idea that Einstein had said the cosmological constant was a terrible idea. You shouldn't talk about it. Or as my mother said, "Do you think you're smarter than Einstein?" I said, "No, no, Mom, no." So this was terrible because we had to be confident enough that we would stand up and say this outrageous thing that the universe was accelerating, which was very surprising. And there was another team, and they had data, and if we didn't do it, maybe they would do it. So we worked very hard and got our publication out early, and that was, we thought that was the right thing to do. One of the things you don't want to be as an observational astronomer, you don't want to be wrong. You don't want to tell people, I have seen this thing, and it turns out not to be true. Or as I told Adam, I think that the punishment for being wrong should be as big as the reward for being right. So you want to do a job that's reliable, and you want to report something that's accurate. You want to make sure that the statistics justify what you say and that you haven't forgotten something or made some error. And so we were, in those early months there in 1998, I would say it was very upsetting that this picture, that the data were telling us that we lived in an accelerating universe, and honestly, I did not like it, and I thought it had the risk of being a really embarrassing thing. So it's worked out okay that 10 years later, the data's much better, the results quite solid, and there are many other lines of evidence that are converging on this same view. Nevertheless, there's that moment where you're kind of afraid of the new thing, and you don't want to be wrong, and you don't want to be embarrassed. Nevertheless, eventually the data gets good enough, and usually it's the kids on the team, the graduate students and the postdocs who say, "Oh, come on, here's the data, look at the data, never mind what you think, look at the data." So really new things in science are a little upsetting and kind of hard to come to terms with. And for this thing, I actually was resisting it for a while. So it's turned out okay. In the end, I've come to like it. And this is the universe we live in, or at least the universe we think we live in, one that has this remarkable thing, this dark energy, which is most of the universe, that we live in a universe that's accelerating, and that may be going into this kind of empty, cold future. When I was in high school, I grew up in suburban Boston, out in Sudbury, and it was a good high school. I was good at math, and I was good in science. I had a neighbor who had a telescope, and he had a little trouble setting it up, and so he asked if I would help him do that, and we figured out how to point the axle at the North Pole and how to do all those things, and it was kind of exciting to look through a telescope and see things. What I did not understand at that point was that there was actually something to do. That is, it wasn't just about seeing them and just about kind of knowing or looking at a natural history book, that you really could understand what those objects were. That didn't come to me for a while until I was in high school, and I remember kind of reading books that Fred Hoyle had written, reading books that George Gamow had written, popular science books that kind of tried to bring you up to speed on what scientists were thinking. And that really got me going. So when I got to college, I came here to Harvard. As a freshman, I took a freshman seminar that was about astronomy, and I've never really looked back. And I've written a book. So, maybe some kid will read it and, would have made a perfectly good investment banker, but, goes astray and becomes an astronomer.